Today we're going to be talking about what sets are and a little bit about set theory. So to start out, a set is a collection of items, and there also is not a particular order to these items. So what do I mean by that? Well, here are some examples. So for example, 2, 3, 7 is the set S, and these sets, I use these curly braces to represent them. Another example of actually the same set is 3, 2, 7. Why is this the same? Because the elements of the set, the items within the set are the exact same, but the order is like swapped. Okay, so sets, they don't actually have to only contain numbers, they can contain other objects as well. So for example, in this case, the set contains the letters A, B, and C. Sets can also contain some combination of numbers, letters, and other sets as well. And sets can be empty. So this is the empty set or null set, and you can write it in two different ways. Both of them are pretty common. So when we're talking about sets, a lot of the times we use this E, like the symbol which looks like an E, and this can be read in English as is an element of or is in. And similarly, just how this is the equal symbol and this is the not equal symbol. This symbol means in or is an element of. This symbol means is not an element of. So for example, this statement right here says that 1 is in this set. And as you can see, that's true because 1 is like clearly inside of it. In this statement right here, this says that the set 1 comma 2 is in this larger set. And that's also true because 1 comma 2 is an element of this larger set. This statement says that B is not in this set. And this statement is obviously true because like we see A, but we don't see B anywhere within this set. All right, so here are some popular examples of sets. So this, as we talked about earlier, is the null set. So there's nothing inside of it. This right here is the set of real numbers. Okay, this right here is the set of integers. So this is a very important set. So here are some examples of integers. Okay, so these are all examples of integers. Here are some non-examples of integers. Here are some numbers which are not integers. It's not an integer. It's not an integer. Not an integer. Infinity is not actually a real number. So these are some non-examples of integers. Okay, n is the set of natural numbers. So these are numbers which are effectively used for counting. So depending on the context, some people, they like to write the set of natural numbers like this. And some people, they like to write it like this. So mathematicians do actually have like some disagreements. I wouldn't say it's like a really big disagreement. But it does depend on who you're talking to. If I ever talk about the set of natural numbers, I will specify whether or not to include 0 or to not include 0. All right, Q is the set of rational numbers. Okay, so rational numbers can be written as one integer divided by another integer. Okay, so for example, like 2/3 is a rational number. Like -2/3 is a rational number. C is the set of complex numbers. And complex numbers are numbers which can be written as a plus bi. Okay, where a and b are real numbers. So for example, a complex number can be 3 plus 2i. Another complex number can be 3 minus 2i. Another complex number could just be 3. Why is 3 a complex number? Because it's technically the same thing as 3 plus 0i. So just to clarify, I is the imaginary number, which is used to represent the square root of -1. Okay, so now when we're talking about sets, oftentimes we use this thing called set builder notation. So let's go ahead and look at this first example. The way this reads in English is like the following. The set of numbers x, this symbol right here means such that x mod 2 is equal to 0. What does x mod 2 equal to 0 mean? It means when I take a number x and I divide it by 2, I'm going to get a remainder of 0. So what numbers are those? Those are even numbers. Like when I divide a number by 2 and I get a remainder of 0, that's an even number. So, okay, the set of numbers x such that x is even. So this is how you read it in English. Okay, so just to reiterate, this symbol right here is equal to such that. Sometimes you're going to see people write set builder notation in a different way. So here's another very popular way in which people write it. In this context, the slash is the same thing as such that. And sometimes, instead of writing such that like these colons or the slash, sometimes people just write it with the abbreviation ST. So you'll also see people write it like this: X ST X mod 2 is equal to 0. All right, so now let's go ahead and go on to the second example right here. So the second example includes the numbers x such that x is even and x is between 0 and 10, not including 10. So if I were to just write out the elements of this set one by one, they would look like this: 0, 2, 4, 6, and 8. Okay, so now let's say that I have two sets, right? So a common thing which people do is they take the intersection of these sets. So this symbol right here, we read it in English like intersection. So right here, this we read it as A intersection B. So A intersection B just takes whatever elements are common to both A and to B. Okay, so for example, let's say I have my set A like this. And I have my set B like this. So what elements are common between the two sets? So 2 is common between the two sets, and 6 is common between the two sets. So I can say that A intersection B is equal to 2 comma 6. Another common set operation is called union. So in English, this reads like union. So A union B takes, okay, A union B merges not the common elements, it just merges all the elements from A and B. So for example, if A is this set, and B is this set, then A union B is just going to keep track of everything which is in both of the sets. So I'll first write this problem, but I'll like say what the mistake is with this. Or I'll like first write A union B in an incorrect way, but I'll say what the mistake is. Okay, so the thought process is I take the elements from A, and then I just tack on the elements from B. So this is actually incorrect because some elements are repeated twice. Like 2 is repeated twice here, 3 is repeated twice, 7 is repeated twice. So in a set, every element, every item in the set, it has to occur only once. So this is actually incorrect. The correct way is to do it like this. Okay, so as you can see, the set A union B is the set of all the elements from A and B merged together. Another set operation is the set difference operation. The way I read it is A minus B. I just read it as a minus sign. So this includes the elements of A which are not in B. So what does that mean? Let's go ahead and look through an example. Okay, so again, we're including the elements of A which are not in B. So let me just mark the elements in common between the two. That should help out a bit. So 2 is in common between both of them. 4 is in common between both of them. And 6 is in common between both of them. That means A minus B includes 1, 3, and 5. It only includes like the unique elements of A. All right, and actually, I would like to just draw a picture for this too. So let's say that I have my set A and I have my set B. Then this inside portion right here, I can write it as A intersection B. And this region right here, I can write it as A minus B. Okay, so that's hopefully gets you some conceptual understanding. All right, now I can also take the complement of a set. So this is in the context of a particular universe U. So this box you can imagine is our universe U. And this shaded region, this shaded circle is our set A. So everything outside of this circle is AC, A complement. Again, the way I read this is like A complement. Okay, so for example, let's say that our universe is these numbers. Okay, so our universe is the numbers between 1 and 6. Maybe in the context of rolling a dice, a 6-sided dice, this would make sense. And let's say E is the set of even numbers. Okay, so then in context of this universe, E complement would be the following set. So everything in the universe except these. Okay, so 1, 3, 5. Oftentimes when we're talking about a set, we are interested in the size of a particular set. So I said subset, but we're interested in the size of a particular set. So for example, let's say I have a set A, and this set is equal to 1, 4, 6. As we can see, we can count out 3 elements in the set. So we say that the cardinality, in English, this reads as the cardinality of A. So we say that the cardinality of A is equal to 3. So when we have like 2 sets, we can take the Cartesian product of those sets. So let's go ahead and read this slowly. So the Cartesian product of A and B, that's how I read this symbol up here, is equal to the set of ordered tuples A and B such that the first element A is from A and the second element B is from B. Okay, so let's go through an example. Let's say that A is the set 1, 2, and B is the set, let's say like 2, 5, 6. Then the Cartesian product of A and B is just the following. It's 1, 2, 2, 5. Wait, let's. Okay, 1, 2, 1, 5, 1, 6. I'm going to keep writing more. 2, 2, 2, 5, 2, 6. All right, so another thing which is which we can talk about is the power set of a set A. So before we do that, let's talk about what the subset of a set A is. So let's just say that I have a set A, and this is equal to like 1, 2. Then I can say that this set, let's just call this set like B. Let's call this set C. And Yeah, and then I have the empty set. So I can say that, for example, B is a subset of A because it includes elements which are found in A only. I can say that C is a subset of A. I can say that the empty set is a subset of A. And I can say that A itself actually is a subset of A. Okay, here's an example of a set which is not a subset of A. So 1, 3 is not a subset of A because 3 is inside of D and 3 is also not inside of A. So D is not a subset of A. All right, so now let's go ahead and talk about what the power set of a set is. So it's the set of all subsets of A. So the power set of A is equal to the following. It's equal to the empty set. It's equal to the set 1. It's equal to the set. Sorry, I'm saying this wrong, but inside the power set of A, we have this set and we have this set. So the power set of A contains all elements of all the elements of the power set of A are the subsets of A.